Okay, so continuing with the third video for 7.3, definition. Okay, so the zero vector, that's what we're defining. The zero vector. Denoted by zero with a vector symbol over it is, how do I want to say this, is given by the zero vector is component 0, 0 and has no direction. Well, it has neither, actually, neither magnitude nor direction. Neither magnitude nor direction. It's a single point, right? So its dimension is 1, not 2. Okay. Oh, actually, let me note something before I go on. So let's note the zero vector is not equal to the number 0, because 0 is a real number. 0, the number 0 is a real number, and the zero vector is not a real number. It's something completely different. Okay, so properties of vectors. Yeah, and here's where things get really long. I'm going to have to list a whole bunch of stuff, so just bear with me. Properties of vectors. We will get beyond this. Okay, so let's let vectors u, v, and w be vectors. And let's have c and k be real numbers. So here we go. Number 1, the first property of vectors. If I multiply 1 times a vector u, that's a scalar 1, I just get the vector u. Number 2, 0 times any vector u turns out to be the zero vector, and we'll prove that in a moment. Number 3, u plus v is the same as v plus u. Oh my goodness, I can't take it anymore. V plus u. Okay, so number 4, if I have u minus v, now that is not associative, but it is u plus a negative v. Number 5, if I have u plus v, and then I add to that vector w, that's the same as adding u to the sum of v and w. So this is, doesn't matter what order I add vectors in, it's still the same result. So number 6, let's say I have k times c times vector u. Then that's the same as k times c times vector u. Or it's the same as c times k times vector u. So any order, they're all the same. Number 7, let's say I have u plus the zero vector. Well, that's just u. Number 8, if I have u plus a negative u, that is the zero vector. Number 9, if I have some scalar k times the sum u plus v, I can distribute, so it's k times vector u plus k times vector v. And number 10, if I have the sum k plus c times vector u, I can distribute as well. So this is k times vector u plus c times vector u. Okay, so these are lots and lots of properties of vectors. But let's go ahead and prove a couple of them. So let's prove, okay, well, for example. So prove the following properties, the following vector properties. Properties of vectors. Okay, so number 1, let's prove that 1 times any vector u is vector u. Well, that's kind of silly, but here we go. Let's let vector u be x comma y. So this implies that the scalar 1 times vector u will be 1 times x comma y, which according to how we do scalar multiplication is 1 times x comma 1 times y, and that's just x times y, which is vector u. So check mark, we've proved that one, which seems kind of silly, but that is a proof. So number 2, let's go ahead and what shall we prove? 0 times u, so the constant 0 times vector u is the 0 vector. So in this case, I'm going to let vector u, once again, let's have it be x times y. So that means that the scalar 0 times the vector u will be the scalar 0 times x comma y, which means I just multiply each component by 0. So 0 times x comma 0 times y, and 0 times any real number is 0, so it says 0, 0. And notice 0, 0 is the 0 vector, not the number 0. So check mark, we do get the 0 vector. Okay, so what else should I do? Which one should I do? I could do number 7. Number 7 is good. So u plus a 0 vector is u. So number 7, I'll call this number 3. So let's do u plus a 0 vector is vector u. Okay, so let's let vector u be equal to x comma y. So that means that vector u plus the 0 vector will be equal to x comma y plus 0 comma 0. Okay, so adding vectors, I just add their components. So this is x plus 0 in the first component, comma, y plus 0 in the second component. And since x, y, and 0 are real numbers, this just gives us x, comma, y, which is indeed vector u. So check mark, we've proved that as well. Okay, so I think that's sufficient. I think you get the idea. Okay, so what shall I do? Should I end this video here? No, let's continue on. Okay, so let's recall. What did we have? We had a sine of an angle theta was y over r if I'm not on the unit circle, right? So what this means is that I can cross multiply and say, okay, well, y is r times sine of theta. Similarly, I know that cosine of theta, if I'm not on the unit circle, was x over the radius. So that means that x can be written as r times cosine of theta. Remember that? Okay. And let's note for a vector v being equal to a comma b, this implies that the radius or magnitude of v is the square root of a squared plus b squared. We know that. So therefore, x, which we know to, actually, let me do it this way. So therefore, a, which is going to be radius r times cosine of angle theta, is going to be the radius is the magnitude of v times cosine of theta. What are you doing, kitty? Cosine of theta. Whereas b, and I would like to change these colors a bit. Let me change these so that this makes more sense. Let's call this A and B. I think that'll be clear if I do it that way. So let's change this to purple. Purple. Okay, so I think that makes a bit more sense maybe. So radius here is green, so we can see where I'm getting this from. Okay, so now B, which is equal to r sine theta, well, that's going to be, r is the magnitude of v times sine of theta. Okay. So notation. Notation. I'll do that in purple. Notation. So another way to express a vector v, another way to express a vector v equal to a comma b is in what we term algebraic form. So let me underline that. Given by. So vector v would be a times I plus b times j. This is the algebraic form of a vector. Okay, so for example, let's find vector v. Vector v in algebraic form. Algebraic form given that the magnitude of vector v is 6 and the angle theta is 7 pi over 6. Okay. So we want to find let's do A and B. So I know that A is going to be the magnitude of the vector v times cosine of the angle theta, because A is the x component. So for us, what does this give us? This gives us that A is going to be, the magnitude was given as 6 times cosine of the angle was given as, for the direction, is 7 pi over 6. So cosine of 7 pi over 6, and I probably should have skipped a line there. Okay, so what is cosine of 7 pi over 6? Well, that's in quadrant 3. So I know it's negative, and it is a 30-degree reference angle, so it's negative root 3 over 2. And of course, 2 goes into 6 3 times, so the horizontal component for this vector is negative 3 root 3. Let's do the same thing for the horizontal component. So b is going to be the magnitude of the vector b, now times sine of the angle theta. So we have that b is going to be 6 times sine of 7 pi over 6. Okay. So we have that b is going to be 6, and in quadrant 3, sine is negative, and at the 30-degree reference angle, it's 1/2. So 2 goes into 6 3 times. So we get that the horizontal component b is going to be minus 3. So therefore, vector v in component normal form would be negative 3 root 3, comma, negative 3. But in algebraic form, that's going to be negative 3 times the square root of 3i plus a negative 3 times j. So I guess we could write that as negative 3 root 3 I minus 3j. That's the algebraic equivalent to the vector form you see there. Okay. Okay, so let's recall. I think I can get all of this done, maybe. I don't know. Do you know what? No, I think I'll stop here and I'll do another video.